Thank you very much. Everybody can hear me, I assume? Good. Yes, I want to tell you about some experiments that we carried out at University of British Columbia last year, in which we measured the radiation from a horizon. The radiation first predicted by Stephen Hawking way back when. But before that, as with any show these days, I have to give an advertisement. Tomorrow night, for any of you that are interested, there's an absolutely wonderful concert of medieval music by these two people, Elizabeth McIsaac, and the other person just happens to be my wife. This is at the Canadian Cultural Centre, so if you're at all interested in early classical music, this is very well worth going to. Let's go to remind ourselves that in 1974, Stephen Hawking predicted that black holes should not be black, but instead should emit radiation with a temperature proportional to 1 over the mass of the black hole. There are various coupling constants that come into it, C's, H bars, Boltzmann constant, capital G. In my talks, I tend to always work in units in which C equals H bar equals Boltzmann's constant equals capital G equals 2 pi equals 1. The last one because I can never get my 2 pi's right. Now, this discovery was a complete surprise. One would have expected that when black holes form, that changing structure of the space-time could well produce particles. Just as, for example, a changing refractive index will produce electromagnetic radiation. A changing background geometry, it would produce radiation. But everybody expected that radiation to die away. But when Stephen was doing the calculation about how much radiation should come out, lo and behold, he discovered that it didn't die away, and it kept producing radiation with that temperature proportional to 1 over the mass. Now, what's really important about this is that that temperature is proportional to 1 over the mass, i.e., it's a function of the energy. It's not just some arbitrary temperature, but it's a function of the energy, and therefore one can look at, just using the elementary. It's probably better if I don't point at my screen of my computer, because you probably can't see much. That allows us to stick the temperature into the TdS equals dE. The heat flow is equal to the energy. Since T is a function of E is just mc squared, which in my units is just m. And we can integrate up this equation given that temperature, and that tells us that the black hole should also have an entropy proportional to 1/4 of the surface area of the black hole. This was not quite as big a surprise as one would have expected. Because back in about 1970, Jacob Bekenstein, who I hear you're having as a visitor later this week, predicted that black holes should have an entropy. Now, his prediction was a little bit shaky. It was sort of an analogy. Stephen Hawking and Dimitris Christodoulou had shown that there was a certain aspect of black holes that if you believed that there was positive energy, that only positive energy could exist and would flow into black holes, this aspect of black holes always increased. Christodoulou called this the irreducible mass of the black hole. Stephen Hawking recognized it as the surface area of the black hole, that this must always increase. Now, therefore, we have the logic which says that if this always increases, and we know that entropy always increases, then they must be the same as each other. Of course, as a logical statement, that may have a little problem with it, but he tried to play with that. He ran into many troubles. One of the things was when he presented this was that Bob Garosh said, look, seems to be a problem here, because surely I can, if that were an entropy, surely I could violate the second law of thermodynamics. I do it as follows. I fill up a box full of radiation. I lower that box down towards the black hole, just as we have here. There's a tension in the rope. That tension in the rope now does work. So I can extract the energy of that radiation in the box by slowly lowering it down towards the black hole. I lower it very, very close to the horizon of the black hole, and in fact, if I lower it just next to the horizon of the black hole, I can extract an arbitrary amount of the energy inside the black hole, inside the box, in this as useful work. Now I open the box and I let the radiation fall in. That radiation has entropy, so that entropy falls into the black hole and disappears from the universe. But when he did this in 1971, 1972, black holes don't have any entropy. Therefore, and in particular, when I allow this radiation to fall in, I've extracted all of its energy so the black hole doesn't change at all. Therefore, its entropy doesn't change. Therefore, we've just violated the second law of thermodynamics. And this bothered Jacob a lot, and he tried to find and wiggle his way around this to get out of it, and could never quite, do it. Until Stephen Hawking showed that these black holes themselves do have an entropy. This, of course, still leaves this argument, one asks about this argument, well, surely I can still extract all of the energy from this radiation inside the box, and therefore violate the second law of thermodynamics. The answer actually is no, because it turns out that if you're accelerating something very near the horizon, just as if you're accelerating something in flat space-time near the if you're accelerating something in flat space-time, you find yourself surrounded by a thermal bath. Now, because you're being accelerated upward, as Einstein taught us, you think there's a gravitational field around you. We now go back 2,000 years, 2,500 years to Archimedes, who taught us that if you take a body and you immerse it into a fluid in a gravitational field, Archimedes, of course, didn't feel it necessary to point that out because everything is always in a gravitational field, then that box will feel a buoyant force equal to the weight of the displaced fluid. Well, that buoyant force equal to the weight of this displaced fluid, i.e. this thermal flux of particles that the accelerating box sees right near the horizon, means that the tension in the rope is less than you would have calculated from the naive prescription. That means you can't extract all of the energy from the radiation in the box. There's always an irreducible amount. The best you can do is to lower that box just to the point where the tension goes to zero. After that, you would have to do work on it to push it in further. When you go through the algebra, you find that that's precisely what you need in order to save the second law of thermodynamics. The amount of energy that you extract from the box is not all of its energy. That excess energy falls into the black hole, increases the surface area of the black hole, increases the entropy of the black hole, and one can show that that increase in entropy of the black hole is always bigger than the entropy of the radiation inside the black hole. Well, that's great. Everything fits together very nicely. One has huge controversies that still rage Well, they rage less now, but there's still a few of us over on the other side as to what the entropy of a black hole really is. Is it the standard kind of entropy that Boltzmann and Gibbs and Maxwell taught us about, namely just a result of the statistical mechanics of some internal degrees of freedom that we don't know about or that we can't measure? Or is the entropy of a black hole something fundamental? One can argue this many times. One can write popular books on it, etc. It's still an open question. But I could spend the whole lecture on this, but that's not the point of my lecture. So we'll leave that aside and let you look up that controversy yourself. Let's go back, however, to Hawking's derivation. And you quickly realize that Hawking's derivation really makes no sense. It's just physically, it's mathematically perfectly correct, but it's physical nonsense. Why is it physical nonsense? Well, let's look at how Hawking did his calculation. He said, let's look at the radiation coming out at late times here. So this is supposed to be time running up this way. Space is these coordinates. This green stuff is supposed to be matter that's collapsing to form a black hole. This black line is supposed to be the horizon, namely a sphere of light which originates in the center, which expands outwards, and because of the positive energy in this infalling matter, it gets focused so that the light rays are just parallel to each other when they exit the surface. That gives you this horizon of the black hole. Since that's light trying to go out as fast as it can and not getting anywhere, nothing can cross the surface from inside. So if we take this radiation going out into the future and ask where could it have come from, well, stuff happening now happens now because of what happened in the past. That's what physics is all about. So we have this radiation escaping here. As we go into the past, these light rays come from closer and closer to the black hole. However, they can't come from inside the black hole, so they get exponentially squeezed up against this horizon. So if the radiation coming out has a frequency of omega 0, then the frequency in the initial state of these light rays as I pass them back has a frequency which goes as omega 0 times the exponential of the time since the black hole was formed that this radiation comes out, divided by a typical time scale for the black hole, which for a solar mass black hole is about 10 to the minus 5 seconds. So if we ask where does this radiation come from for a solar mass black hole, and we look 1 second after that solar mass black hole formed, then it has a frequency that radiation had or was quantum fluctuations in the initial state whose frequency was omega 0 times e to the 10 to the 5th. Now e to the 10 to the 5th is a very large number. In fact, it's such a large number that no matter what units I stick onto this frequency, it makes no difference, because those units simply transform this 10 to the 5th by some tiny little amount. So therefore, if I measure this in Planck scales or in Hertz, or in, if h bar omega is the mass of the whole universe, it makes no difference. This incoming radiation had a frequency that was e to the 10 to the 5th times that. So it has an effective energy, these incoming fluctuations, of e to the 10 to the 5th times the mass of the whole universe. Now, the fundamental assumption that Hawking made was that these were quantum field theories, free quantum field theories, in which there was no gravitational effect of the quantum fields that were coming in. Clearly, if I've got a fluctuation whose mass is e to the 10 to the 5th times the mass of the whole universe, sitting anywhere near a solar mass black hole, the approximation that that doesn't do anything is a really bad, really bad approximation. So, does that mean, so this just points out that if it comes out as e to the I omega t, when it comes in it looks like this, which is a very singular function, just near t goes to t0. Now, if one could do experiments, of course, if one had a small black hole and one measured this outgoing thermal radiation, that would tell us that doesn't matter what kind of absurdities one's carried out, it's right. And it's up to us to figure out what the problem is in our derivation, not nature's problem to figure out, why in the world it evaporates. Unfortunately, small black holes are really hard to find, so it's hard to do these experiments. Back in 1972, when I was a postdoc of Roger Penrose, Dennis Schauma at Oxford asked me to come to Oxford to give a colloquium on black holes. Black holes were new objects at the time. John Wheeler had just named them a few years before that. A lot of people didn't believe they existed. This whole idea that in astrophysics black holes exist out in the universe was not something that almost anyone believed. Astrophysicists laughed at the general relativists about black holes. What in the world are these things? They're obviously some fancy theoretical imaginations. Anyway, I was trying to give a colloquium in which I was trying to explain what black holes were all about. And I came across an analogy, I thought up of an analogy, which was imagine that you're living in a world and these are fish, and those little things there are not fins, they're ears. These fish happen to be blind and they experience their world only through the sense of sound. Now in this world there happens to be a waterfall. And that waterfall is a particularly virulent waterfall, such that at some point in the waterfall, the velocity of the water is equal to the velocity of sound in the water. In our world, of course, that's a little hard because the height of this waterfall would have to be about 10 kilometers in order to pick up enough velocity for it to be going faster than sound. But let's imagine we're living in Terry Pratchett's Discworld. I don't know if any of you have ever read Terry Pratchett. It's a world in which magic operates. But one of the things is that light and various things all travel much more slowly. So here we've got this place where the velocity of the water equals the velocity of sound. And let's assume these fish are very intelligent fish. In fact, they're physicist fish. And they're trying to understand the world around them. And in particular, they're trying to understand this waterfall. And as usual, the professor here sends his graduate students to try and investigate this waterfall. Now, if that graduate student yells out to the professor out here, we know that the velocity of the water is going to sweep the sound over towards the waterfall, but sound travels faster than the water, and so the sound going outwards will get to the professor. The stuff going inwards gets swept over a little bit faster. If, however, he happens to emit the sound just as he's going across this horizon, then the sound waves traveling outwards are swept over at the same rate as the sound is trying to get in. So the successive sound waves just at this point will just pile up on this horizon. The stuff going in the opposite direction will be swept over the waterfall. If the graduate student yells afterwards, then of course the sound is just swept over faster than the sound wave is traveling out and goes down to the rocks below. Furthermore, this surface then acts very much like the horizon of a black hole for sound, just as the horizon of a black hole is a horizon for light, i.e. sound cannot get out of this surface. One of the aspects of black holes that we all know about is that if you fall into a black hole, the light that's given off by you gets redshifted. Similarly here, because the sound takes longer and longer to get out, fighting up against this water, the closer to that surface you emit the sound is base shifted. So that if this poor fish was yelling, "Help!" just as he was swept over the waterfall, all that would come out to the fish outside would be something like, "Help!" as the sound got base shifted and the last few syllables never actually got out. So just as with light near a black hole, it behaves like sound near the black hole. Well, this was a fun sort of analogy for giving talks, but it was nothing more than that in my mind until about 1980 when I was given a course in fluid mechanics to teach. And one day while I was preparing my lectures, my mind wandered and I started thinking about this analogy that I had used and asked, well, how would the sound waves behave in the vicinity of this flow over the waterfall? And what I found was that, in fact, if the fluid is irrotational, so the velocity of the fluid flow is just the gradient of some background of some potential, fluid potential, and one looked at the small perturbations in this potential, one found that potential obeys just the box on phi equals 0, where that box operator is just the Laplacian given by not the flat background space-time metric, but by a metric determined by the velocity of the fluid itself. So that the time component of the metric looks like c squared minus v squared. Notice that that goes to 0 when v is equal to c. The time-space components turn out to be just the velocity, and the space-space components are flat. If one chooses this background flow to be radial, and one chooses the form to be just the velocity of sound times the square root of 2m over r, then this turns out the metric that goes into this Laplacian turns out to be exactly Schwarzschild metric in a special kind of set of coordinates called the Pan-Levy-Goulstrand coordinates. Pardon? I'm sorry. Yes. Thank you. I keep getting his name wrong. He was actually trying to prove that general relativity was nonsense. Anyway, he's come back to haunt us. Whoops. We'll get there. Well, now one can go back and use Hawking's arguments. And one can follow Hawking's arguments step by step in this, for the sound waves in this metric, exactly as one did for a scalar field in the Schwarzschild metric. And one finds that every single step of the argument goes through, which tells us that this system must emit thermal radiation. The temperature of the thermal radiation is, of course, not 1 over the mass of the black hole, since this thing doesn't really have a mass, but it's related to the properties of the fluid flow. In particular, it's related to just the spatial derivative of c squared minus v squared, where that's the velocity of sound, that's the velocity of the fluid. If this happens, if the velocity of sound is a constant, of course, this is just proportional to the derivative of v divided by x. 1 over 2 pi times the derivative of v divided by x. If one wants to stick in the h bars and c's, there's an h bar divided by Boltzmann constant that multiplies this expression. The problem is that in this hydrodynamic approximation, one gets exactly the same problems as you do with Hawking's derivation. Namely, that the radiation emitted at late times is caused by the vacuum fluctuations with frequencies of e to the some large number in the earlier times. Well, we know for sound waves that that's nonsense. Once a sound wave has got a dimension less than the interatomic spacing, you can't have sound waves. So there's a natural cutoff for sound waves. So the question we can ask ourselves is that natural cutoff, is that going to destroy the whole effect, or is it going to remain? I thought of this, and that was the paper that I published 30 years ago. The problem was I didn't know how to answer the question. I just saw that we had, I would have to solve the equations for 10 to the 23rd atoms, all going over the waterfall and look for the sound waves in this, and that just seemed an impossible problem to me. And it was Ted Jacobson who realized that one of the key things about the atomic nature of matter was that it altered the dispersion relationship for the sound waves. Instead of omega just being proportional to the wave number k, omega in general is proportional to some function of the wave number k. If one looks at the dispersion relationship in the flowing water, then omega is going to be that function minus v times k, where v is the velocity of the water. This is in smooth flow. Well, this allowed one, this is just an example of the kinds of dispersion relationships we get. For example, we've all done the problem of a number of masses on springs, and you calculate the normal modes of those masses. And then omega as a function of k looks just like the sine function. There's, of course, the other, the terms for these sound waves going in the other direction, which is the sine function going in this other direction. If one asks the experimentalists for liquid helium-4, they've measured the dispersion relationship of sound waves in liquid helium-4, and you get a dispersion relationship that looks something like this. This dip in here is called the Roton dip because it was once upon a time thought that that part of the dispersion relationship was due to some sort of vorticities generated in the liquid helium. It's almost certainly just simply short wavelength sound waves that are caused by the next to nearest neighbor interactions between the various helium atoms in the fluid. This scale here gets close to the interatomic scale. Once you get to the interatomic scale, you find that the dispersion relationship just becomes a mess, as you would expect. Sound waves whose wavelength is equal to the spacing the average spacing between the helium atoms become very hard to define, and their dispersion relationship becomes hard to define. So for all of these materials, we get dispersion relationships that vary from the nice linear relationship that you get for sound waves at low frequencies. This turns out to be crucial. And one can do, for example, numerical experiments on this and ask whether or not those numerical experiments lead to a thermal spectrum. And after talking with Matt Choptewek, who's now at UBC and one of the world's experts in numerical calculations, I realized that perhaps one could actually do this calculation without running into instabilities, and discovered that, lo and behold, yes, one still got thermal radiation. In this case, one never gets the frequencies or the wavelengths becoming those absurdly high numbers. They get cut off by the dispersion relationship. They actually never even get down to this interatomic spacing. They always sit up around here. Despite this violent change from the Hawking procedure where you got those absurd numbers, you still get exactly the same temperature. at least in these numerical experiments, these numerical calculations. Well, back in 1981, I published this paper about the relationship between sound waves and these analogs to black holes, which since then I've called dumb holes. Now, you're not to think of the word dumb in the usual modern sense. It's from deaf and dumb, meaning unable to speak. In English, unlike, I guess, in French or German or whatever, the two words, stupid and unable to speak, have exactly the same form. So you're not supposed to confuse it. The thing I want to point out here is this question mark. Now that's a genuine question mark. One of the things about the question mark was that I had to fight hard with the editors to get it through. You will notice that the editors of Physical Review D do not like question marks and titles. The other thing, and probably this is the reason why, this question mark violates Scott Tremaine's dictum, which is that anytime you get a paper with a question mark in the title, the answer is always no. Well, in this case, that wasn't true. This was a genuine question mark. Maybe it might be possible that one could do experiments on these kinds of analogs. To a certain extent, I've spent the last 30 years of my career erasing a question mark. So in 2010, the paper was actually published in Phys Rev Letters just at the beginning of 2011. I don't know why it took them so long to publish it. We could have titled the paper just Experimental Black Hole Evaporation without a question mark, but instead this is the title of the paper that we published. And this is the group of people that did the experiment. It's an interesting group of people. I'm a theorist. Silke Weinfertner was my postdoc, is also a theorist, student of Matt Visser's in New Zealand. Matt Penrice was an undergraduate student that was doing his senior thesis on this, and I also hired him during the summer to work on this. Greg Lawrence is a professor in the civil engineering department. And Ted Tedford was his graduate student, and we hired him as a postdoc in order to carry out this experiment. So there was a whole sort of cross, and Silke's from Germany, these guys are from Canada. At the beginning, we also had a graduate student from Brazil who briefly helped us. So there's a very international cross-disciplinary effort to carry out this experiment. And I want to spend the rest of the time talking about the experiment. So from that 1981 paper, variety of situations, one could show that one could get analogies in all kinds of situations. Sound waves, surface waves, electromagnetic waves in a waveguide or in fibers. All of these things obey the same equations as Hawking, as a scalar field does in a background, and all of these, we could follow Hawking's derivation. All of them differ from Hawking's theory only at short wavelengths. Despite that difference, all of them would be expected to show a thermal spectrum of radiation coming out. But what this means is that one can use these differences to test the dependence of the effect, of Hawking's effect, on that short wavelength physics. Does the thermal radiation from black holes really depend on that ultra short wavelength physics, or doesn't it? So in the particular experiments that, one of the things that I'm going to use crucially in the following is some elementary quantum mechanics. And the way I want to phrase this is by looking at a generic amplifier. Now, what's an amplifier? An amplifier has an input, which I call x, with its conjugate momentum p. It has an output, which I call y, with its conjugate momentum p sub y. Now, this amplifier, the amplifiers I'm going to be interested in are called phase-insensitive amplifiers, i.e. they amplify both x and p in exactly the same way with the amplification factor A. The problem is that if these are genuine momenta and position coordinates, then y and p should obey the standard quantum commutation relations, just as x and p, little p, do. Well, if I go ahead and take the commutation relationships between y and p sub y, that's going to be a squared times the commutation relationships between x and p, which is just I. Well, that's supposed to be equal to I as well. So that would seem to suggest that the only possible amplifier that one can have in the world is an amplification of 1. Well, that is experimentally shown to be nonsense every time I go into my living room and I turn on my hi-fi. I turn the little volume knob and it gets louder. That amplifier works. So what's wrong with this? Well, what's wrong with this is that in general, an amplifier cannot have simply one input. An amplifier, in fact, always has to have at least 2 inputs. In this case, a thing I call x and q, and the conjugate momentum to q I'm going to call theta here. If I choose my output to be this combination of x and q, similarly, it's phase insensitive, so it's got the same kind of combination of p and theta, except notice here that this is a phase inversion in the q and theta plane, i.e. q gets amplified by b, but its conjugate momentum gets amplified by minus b. There will also be another output, which has to, from commutation relationships, has to have this form. If I now look at the commutation relationships between y and p sub y, that's now equal to a squared minus b squared times I. And that can be equal to I as long as a squared minus b squared equals 1. Well, a squared minus b squared equals 1 means that a is cosh of something and b is sinh of something. That's easy to arrange. Notice that these coefficients a and b are completely classically determined. I feed in a classical signal into x. I read the output in y, and that tells me what a is. You know, I listen to my hi-fi stereo as I turn the knob, and that tells me what a is. However, if I now look at the quantum noise coming out of this system, i.e. I feed the vacuum state for x and q into the system and ask what comes out for y and p sub y. Well, what comes out for y and p sub y is a thermal density matrix. That thermal density matrix has a thermal form with a lambda coefficient here. It's negative, we notice, because b is always smaller than a, so that's a negative sign in there. This thing acts like omega over kt. So this density matrix is a thermal density matrix with omega over kt, just given by the logarithm of these classically determined factors. Once one looks at the classical behavior of an amplifier, one immediately knows what the quantum output of that amplifier will be simply from quantum commutation relationships. One can also do this with annihilation and creation operators, call them alpha and beta in this case. One goes through exactly the same thing, and one again gets a density matrix that looks thermal, that's proportional to lambda times c dagger c, where lambda again is just the log of beta squared divided by alpha squared. i.e. we get a thermal spectrum coming out, not a thermal spectrum, but a thermal density matrix coming out. How does one determine these A's and B daggers once one has the solution? Well, what one has to use is, in fact, a property of any linear system, namely that there's a norm for that linear system, which is always conserved. That norm is, so these Q and Q are, Q is a solution to the equations of motion, a complex solution to the equations of motion. If I take this combination, one finds that that combination is conserved. If one has more than one oscillator, it's just the sum over all of the oscillator that's conserved. If one has a field theory, it's just the integral of phi star pi, etc., that is always conserved. By choosing one's classical solutions, one finds that the quantum field can be written in terms of A times a positive norm, classical solution, plus A dagger times a negative norm, classical solution. This norm, because of that minus sign, is not positive definite. If Q has got positive norm, then Q star has got negative norm. And the A's and A daggers are associated with positive and negative norms. Now, those of you who've taken quantum field theory have often been you talk about positive and negative frequencies. In most of the situations in which quantum field theory acts, the things that they call positive frequency are in fact positive norm. So it's technically correct, but it's confusing to students because what's really important is the norm and not this positive and negative frequency. Because there are many systems in which you can have negative frequencies but positive norm. I.e., there is no real relationship generically between the norm and the frequency, and it's the norm that turns out to be important for defining the annihilation and the creation operators. But the lesson I want you to take away from this is, in fact, that all of the quantum mechanics for a linear system is completely determined by the classical behavior of that system. Once you know what the classical behavior is, you know what the quantum behavior is as well. And you know what the quantum noise is. Now, if you look at Hawking's derivation, you find that what Hawking did in his derivation was precisely to calculate those A and B coefficients. That the black hole acts like an amplifier of those initial fluctuations. Remember, I said those initial fluctuations had absurdly high frequencies. It illustrates that an amplifier doesn't have to preserve frequencies, doesn't have to preserve energies. All of the behavior of the amplifier is in the behavior of the norm, not of the energy. So the quantum black hole amplifier actually acts as a de-amplifier of energy. The energy coming out has this very low frequency. The energy going in had this absurdly high frequency. So the energy, h bar omega, has crashed down to almost zero. But that thing is still acting like an amplifier. And all Hawking did in his calculation was to calculate those amplification coefficients. So what experiment did we do? The experiment we did was in flowing water, and what we looked at was the surface waves on the water. We had flowing water with an obstacle underneath the surface, so the water had to flow faster over the top of the obstacle. If one arranges the height properly, then in fact one can arrange it so that the velocity of the water over the top of the obstacle is faster than the velocity of these long wavelength waves that are traveling in towards the system. It turns out to be far easier to do the experiment instead of on the black hole horizon, to do it on the white hole horizon. With the black hole horizon, the problem is that you have to send in very short wavelengths, and they get converted then into long wavelengths. Wavelengths of 60 meters or something. Well, it's really hard to measure a wavelength of 60 meters when the total tank one has is a total length of about 3 or 4 meters. However, sending in long wavelength waves and then measuring the short wavelength waves given off by the white hole, which is simply the time inverse of a black hole, is much easier to do. So because the white hole is simply the time inverse of the black hole, one can do all of one's investigations there. And that's what then gave this paper, which was published in PRL in January of this year. This is the experiment. I like this diagram because it reminds me so much of the diagrams that you see in 19th century books. And in many ways, this is a sort of 19th century kind of experiment. There's a water flow in here. There's a pump that pumps water from a holding tank up in here. There's a screen, a set of screens here which condition the flow to remove the turbulence caused by the inflow from the pump. The water flows down this tank over this obstacle designed so that we don't get any separation of flow, and over this weir here and falls into the holding tank again. We can raise and lower this part here to change the depth of the water inside the tank itself. We have a wave generator here, which is a little screen which dips into and out of the water, which then produces the waves, long wavelength waves, which travel back up here. The frequency here went from about 0.02 hertz, in other words, 50 seconds for one period, down to about 0.7 hertz. So we had various wavelengths. The longest wavelength of the 0.02 was about 60 meters. Well, this whole tank is only 5 meters long, and this distance is about 2 meters. So even one wavelength doesn't fit in. But that doesn't matter because this is producing it at that frequency. All that can be traveling up here is that very long wavelength towards that obstacle. Yeah, well, we'll discuss that a little bit. If one looks at the dispersion relationship of these waves, we know what the dispersion relationship of surface waves on water is. In the lab frame, one finds that the velocity of the water turns over the dispersion relationship so that we in fact get a dispersion relationship that looks something like this. Because it's a steady flow, the frequency is conserved. So if one has an incoming frequency in here, one finds that there are only 3 possibilities for the waves traveling on the surface of the water. It can either have a very low wave number, namely long wavelength waves, or it can have these short wave numbers, meaning short wavelength waves. We notice here that the group velocity of these waves, that's just the slope of the curve just here, that group velocity, the way we've defined things, means that these waves will travel upstream against the flow. These 2 waves, however, have a group velocity which is less than the velocity of the flow, so they're both dragged away from that horizon. They're the outgoing waves, and this is the ingoing wave from this side. If we look at the regime in which the velocity of the water is higher than the velocity of the long wavelength waves, this is a case where it's just about equal to them. We find there's only one solution, and its group velocity has those waves traveling towards the horizon. So this one and this one are waves that travel towards the horizon, and these 2 are the 2 modes that travel away from the horizon. And what we want to measure is the amplitudes of these modes. Now, remember I said that as far as the annihilation and creation operators are concerned, what's important is the norm. all of these waves here have positive norm. All of these waves have negative norm. Notice that the positive norm waves can have positive frequency or negative frequency. They're all positive norm waves, and they're associated with annihilation operators. All of these waves have a negative norm, and they're associated with the creation operators. So if one sends in this wave, which is an annihilation operator, and one gets a combination of this wave and this wave, well, that ratio between those two is the ratio between the B operator, between that B coefficient and the A coefficient over here. Remember, the log of that ratio was omega divided by the temperature. This is an ingoing wave, so if we don't have any waves coming in, we can forget about this part of the dispersion relationship. Notice that if one increases the frequency, the ingoing wave number increases, i.e. the wavelength decreases. The outgoing wave number, positive norm wave number decreases, so the wavelength increases. And this outgoing negative norm, the wave number increases. That will become important later on. Since we're using surface waves, we have to be able to measure them. And so one of the questions was, how in the world do you measure them? And one of the standard ways would be to stick little needles in the water or something, use capacitive measurements. But of course, that disrupts the flow. It's much neater to use lasers. This is something they didn't have in the 19th century. So what we got was a little lens, a Powell lens, which spreads the laser beam out in the transverse direction. It keeps it thin in one direction, but spread out by, so on the surface of the water, it's about 2 meters long on the surface of the water here. The problem, of course, if we just shone a laser beam on the surface of the water, is that that would just simply reflect or go down, refract down to the bottom. And if I'm looking at it from the side to try and measure the heights of the waves, one wouldn't see it at all. So what we did was we filled the water up with a dye, a rhodamine dye, which fluoresces in the light of this green laser light, the same kind of light that you get in green laser pointers. And furthermore, we had enough dye in the water so that the optical mean free path was less than 1 millimeter, so one can very accurately measure the location of the surface of the water simply by taking pictures from the side. One of the advantages as well is that because we're looking at the fluorescence, which is incoherent, you don't get the whole speckle problem that you do for laser light as well. So one can really measure that surface accurately. In fact, at first you'd think that what would limit the resolution was the pixels of the camera. So this is 1 pixel, this is the intensity of light, where these are the individual pixels in the vertical direction. So these red little stars would indicate what the resolution would be if one simply accepted the pixels as the limit. However, by taking the intensity of the light in the adjacent bins, one can actually do much better than that. The camera softens the surface, so it's not just a single line, but gets made into a sort of a Gaussian. And by doing a quadratic fit to that with the intensity of the adjacent lines, one can figure out where the peak is to much higher accuracy than 1 pixel. So we were able to measure the tops of the waves down to about 0.2 millimeters by simply using a CCD camera. So this was about 2 meters in length and about 0.2 millimeters in height that we were able to measure the water. Here's an example where we took a picture just of flowing water with no obstacle, and we just looked at the noise. And the black and the red lines are simply the dispersion relationship that we would expect for the water flowing at that rate for waves on the water. And we notice that the noise that we have there is in fact exactly the dispersion relation, follows the dispersion relationship of waves on the surface of the water. What bothered us for a while is that there seemed to be a slight hint, and it's a little clearer when you look at it on the computer screen, that there's another branch sitting up here and down here, which bothered us for a long time until Ted Tedford suddenly realized those are transverse modes of oscillation in the tank superimposed on the longitudinal wave. This is the second transverse mode, and its frequency fits perfectly. The first transverse mode would sit in here. The problem is that the first transverse mode has a node right where the laser is, so you wouldn't see it. The laser only illuminates a 1 millimeter wide strip down the middle of the tank. So our detection system and the height of these waves is less than a millimeter. So our detection system really does seem to work with a resolution down to better than 1/10 of a millimeter once you average out over many wavelengths. This is a little movie showing, this is an old version of the wave generator. This is the dye in the water. It generates the waves traveling up the tank towards the obstacle, which is coming into play here. The wavelength gets shorter, and we notice right about here we've got this horizon. The waves never get through that, and instead you get short wavelength waves that are dragged out. Now those short wavelength waves have exactly the same frequency as the incoming wave, and so you can't really see them as something that's moving. Whoops. End of the movie. But this is, for example, a picture. The false colors are the height of the waves. This is distance along the tank, so that's 2 meters here. And this is the time in seconds. And what we did was we sent in a pulse of waves. Notice the center of the pulse of waves gets near the horizon and turns around. That's the group velocity. Whereas the phase velocity, we notice, stays positive even though the group velocity has turned around. It's a really neat example of group and phase velocity and situations in which one can have a phase velocity which is opposite the group velocity. I always got confused when I was taught phase and group velocity when I was an undergraduate. It was just this funny mathematical expression. Wasn't sure what it meant. And so it would help a lot to use physical examples like this so that the students could understand better. So this is one of our experimental runs in which we sent in waves of a particular frequency. And one of the things we had to do was to make sure that when we did the Fourier transform, so this is the Fourier transform frequency hertz, that we got an exact number of periods in our bins that we did our Fourier transform on. One knows that if one has a sine wave and one doesn't choose an exact number of periods for that sine wave, that when you do the Fourier transform, you get this broad output. You don't get a single delta function, you just get this broadly based stuff coming out. Notice here that in the time domain, there is no breadth. So this is 1 pixel in the Fourier transform. In the next pixels, you see you get virtually no signal. There's a little signal here. Red means very intense. Yellow is less intense. Blue is the least intense. There's a little bit of leakage that we notice in here, but we've done a pretty good job of making sure that the number of periods is exactly, so the time scale over which we're doing the Fourier transform is an exact multiple of the number of periods. So taking this strip for a bunch of different frequencies will now tell us what's going on. Notice here that we get an intense output at positive frequencies, which in this case turns out to be positive norm. This is the incoming wave. Notice we also get an output at negative wave numbers, which turns out to be the negative norm waves. So one is getting these, this is a non-trivial A and B coefficient, which immediately implies that there will be quantum noise. If we take this strip in our various experiments and now plot out the intensity, whoops, these are some of the positive norm waves going out. Notice the phase velocity here. These are some of those negative norm waves going out, and notice that they have the opposite phase velocity of the positive norm waves. So this is the intensity along those strips. There are three samples that we've got here. This is our lowest frequency sample, is the green one. And notice that the positive norm and the negative norm amplitudes are essentially the same. For the next one, 0.18, the positive norm has gotten bigger. Notice its peak frequency has moved in, which is what we expected from our diagram of the dispersion relationship. The negative norm has moved out. Has moved out. And as you go to higher frequency, it moves out still more. Notice that the amplitude of the negative norm decreases with respect to the positive norm as the frequency increases. So one can plot that, and in particular what one wants to plot is the log of the B, the beta, and alpha coefficients, or the B and the A coefficients, which are simply the integrals under the curves of this peak, let's say, and this peak. Then we have to square that to get the norm. And this is a plot of the logarithm of that ratio, which should be that coefficient lambda, omega over kt. So if this thing is going to produce a thermal spectrum, mode by mode we know that it's a thermal density matrix, but if this is also going to be a thermal spectrum, then this thing should be a linear function of the frequency. The temperature should be independent of the frequency. Well, I think looking at these little x's, I think you'll agree that we've got a pretty good linear function of the frequency here. This tells us that if one were to look at the quantum emission of this horizon, it would be producing a quantum emission with a temperature independent of frequency, which was proportional to 1 over 8 hertz, 0.125 hertz. One of the other features, of course, of these black holes is that that temperature is supposed to be related to the properties of the fluid flow just at the horizon. In particular, is the derivative, the temperature is proportional to the derivative of c squared minus v squared with distance divided by 1 over 2c. This temperature, we want to relate, basically, we want to relate this frequency to what we measured in the previous case. And this is our attempt to do so. This is the slope that we got, the frequency corresponding to the slope in that previous diagram, 0.125. Somewhere in here is the horizon. The problem is it's hard to tell exactly where the horizon is. And that means that determining exactly where along this curve I should be taking this derivative is difficult. So the best that I could estimate is that the temperature that's given by this Hawking-like formula is somewhere between about 0.8 hertz, 0.08 hertz, and 0.18 hertz. So about a factor of 2 error in that. Notice that the frequency that we measured is 0.125 hertz, which lies right in the middle of that band. So it really does seem that this system produces a thermal spectrum coming out with a temperature of about 10 to the minus 12 K, or a frequency of 0.125 hertz. What we've effectively done here is measured this effect using stimulated emission, but we know from Einstein and, that once you know the stimulated emission, you also know the spontaneous emission rate. That's another way of phrasing that whole amplifier stuff I talked about. So given that caveat that I'm measuring the classical behavior of this system, I'm measuring a white hole rather than a black hole, but after all, a white hole is simply the time inverse of a black hole. Given those two caveats, and given that I'm looking at an analog rather than a real black hole, given those three caveats, I think I can argue that what we have here is the first observation of Hawking radiation from a horizon of a black hole. And at that point, I'll quit.